All right, this is going to be the first video of Chapter 7, where we're talking about how do we develop chemical formulas and also chemical compounds. It's important that we look at the different rules for ionic compounds versus covalent compounds. Some of them are easier in some ways, some of them are more difficult in some ways, but you do need to be aware that there are two separate types of rules, so we want to make sure that we are um, using each set when it's appropriate. So first off, let's talk about chemical formulas in general. What do chemical formulas tell us? It's really two things. They indicate the number of atoms in a compound and also which atoms are in the compound. For example, if I have this substance octane, C8H18 tells me that that molecule of octane is going to contain 8 atoms of carbon and 18 atoms of hydrogen in one molecule. Now, for ionic compounds, remember, they don't form molecules. Instead, they form um, networks of ions that are together in a structure. So we don't necessarily call um, chemical formulas for ionic compounds molecules. We call them what's called a formula unit, a unit being the smallest whole number ratio between a positive cation and a negative anion. So my example here, aluminum sulfate. Notice it's Al2, and then we have a group of SO4. Remember, that's called a polyatomic ion. It's got one S attached to four O's, and we have 3 of that particular ion. So we've got 2 aluminums for every 3 sulfate ions. What this tells me is that I have 2 aluminums in that compound, 2 aluminum atoms, and the parentheses sort of work like the distributive property in math, where the 3 is going to apply to every atom in those parentheses. So I have 3 sulfur atoms, and I have 3 sets of 4 oxygen atoms, giving me a total of 12. So in that particular formula unit, I'm going to have 2 aluminums, 3 sulfurs, and 12 oxygens. Notice that I don't put a subscript after sulfur because there's only one of those in that ion. The one is assumed. We don't really write it as a subscript. Oops. Let's go back there for monatomic ions. Remember that every element essentially wants to have an electron configuration similar to a noble gas. So we can actually look at the periodic table to figure out what the charge of a monatomic ion would be. Monatomic meaning that there's only one atom in that ion. And my example here is nitrogen. How do we know that nitrogen would have a -3 charge? I can look at P table and decide, is nitrogen better off moving backwards to become like helium, or is it better off moving forward to become like neon? In this case, it would have to go back 1, 2, 3, 4, 5 to become like helium. So instead, it's going to move forward 1, 2, 3 to become like neon. Remember, gaining 3 electrons, electrons have a negative charge. So gaining 3 electrons means that nitrogen will have a -3 charge. So most of these P block elements are going to form a negative charge, with the exception of like aluminum, because you think of aluminum, it could either go forward 1, 2, 3, 4, 5 to become like argon, so that'd be a -5 charge, or it can go back 3, losing 3 electrons to become like neon. That's the simpler route to gain a +3 charge. So aluminum will have a +3 charge. There's actually a simple method to determine that. Um, if we know that group 1 will always have a 1 plus charge, group 2 will always have a 2 plus charge, group 13 will always have a 3 plus charge. It gets a little more complicated in this D block because a lot of these can have multiple charges. So just remember group 1 is +1, group 2 is +2, group 13 is +3. But then we can go backwards. The halogens, the group 17, those are going to be -1. The group 16 is going to be -2, and group 15 is going to be -3. Group 14, why I'm skipping those, they're sort of in the middle. They can go either way. There's going to tend to actually they can form ions, but they're going to more commonly be in covalent compounds. So we're not going to worry about their charge as of now. So just remember the first 3 groups on the left will be +1, +2, +3. And then we go -3, -2, -1. So that is how you can easily find the charge of a monatomic ion. But like I said, carbon and silicon, they're in that group 14 where they're going to tend to form covalent bonds. Naming monatomic cations is really simple. Potassium with a plus charge, we call it potassium. Magnesium with a +2 charge, we're just going to call it magnesium. So for cations, you literally just name the ion what its element name is. However, for anions, the negatively charged ions, we're going to add the word or the suffix "ide" at the end. So instead of it being fluorine, we're going to call it fluoride. And instead of nitrogen, we're going to call it nitride. Oxygen would be oxide. Chlorine would be chloride. Hopefully you get the idea there. That's only for the negative ion, though. Here are some common main group elements there. Notice the positive ones like lithium, sodium, and potassium. They retain their name, whereas fluorine, chlorine, and bromine, they become fluoride, chloride, and bromide. Those negative ones take the "ide" suffix. Now, notice the D block elements, and we're going to talk about this a bit more, but some of them can actually have 2 possibilities. For instance, iron can make a +2 charge, or it can make a +3 charge, and we use Roman numerals to indicate the specifics between an iron +2 and an iron +3. Lead, similar idea. Lead can be +2 or +4. Same with tin. Tin can be +2 or +4. We use the Roman numeral to tell us what the charge is sometimes for positive ions. Now we don't always have to do that. We only are going to use the Roman numerals when there is more than one possibility. If you see zinc here, silver, they don't make multiple ions typically, so zinc will just be zinc, silver will just be silver. And also, just a note, we talked about this a little bit in a couple chapters ago, but anions tend to be larger than the original atom. Cations tend to become smaller because they're losing electrons, they're losing energy levels, so they'll decrease in size, whereas anions are completing their shell, and those electrons will not be held as tightly by the nucleus, which doesn't change. So the first type of compound we want to talk about is binary compounds. These are composed of simply 2 elements, and specifically here, binary ionic compounds. The key here to figure out how to write the formula for a binary ionic compound is that the charges need to cancel out so that the negative charge equals the positive charge. For instance, if I look at magnesium bromide, magnesium has +2 charge, and bromine, which becomes bromide, will have a -1 charge because it's in group 17. Those unfortunately don't cancel each other out. So what I have to do is consider how many anions it will take to cancel out the charge, the +2 charge of the cation. So 2 bromines with 2 -1 charges will cancel out with 1 magnesium with a +2 charge. Therefore, the formula I want is MgBr2. Now, sometimes a trick that you can use to figure out the correct chemical formula is realize that the superscript, the charge of one ion, will become the subscript of the other. So that 2 crossed over and became bromine's subscript, and the 1 crosses over and becomes magnesium subscript. Now you have to be careful because the subscripts need to be the lowest ratio. So for instance, if you had a 2-to-2 ratio, like a +2 charge and a -2 charge, you would need to reduce that down to 1-to-1. But most of the time this will work out for you, where you just flip-flop the charges and make them the subscripts. We'll look at some more examples. Sorry, my PowerPoint's freezing here. And I think this slide will go over crossing over with the example of aluminum oxide. Aluminum, it's in group 13, as I mentioned earlier. It's going to have a +3 charge. Oxygen, which is in group 16, will have a -2 charge. So those are my symbols, aluminum and oxide. I'm going to cross over the charges using their absolute values. So the 3 will go with the oxygen, and the 2 will go with the aluminum. So it'll look like this, Al2O3. Now let's check to make sure that works out. I'm saying that I need 2 aluminums to balance out with 3 oxides. Aluminums are each +3, giving me a total of +6. Oxides are each -2, and there's 3 of them, giving me a total of -6. So it does indeed check out. That's the important thing for naming or giving the formula for ions, is that their charges do need to cancel out. Here's another example with iron 3 oxide. The same idea, where iron 3 has a +3 charge, oxide has a -2 charge. So we flip-flop the charges to the subscripts, and instead of Fe+3 and O-2, we get Fe2O3. Note that I should never see charges in your final compound formula. I don't want to see pluses or minuses or superscripts in the final answer. Your final answer should only contain the subscript that is necessary. So this naming system we call nomenclature. Anytime we have a system of naming things, we call that nomenclature. Even in like biology, when you're naming species, we call that a nomenclature. But the cation always comes first, and then the anion always comes second. A lot of times people wonder how you know which of the 2 ions will come first. We always go positive and then negative. So for that example in the last problem, we had Al2O3. That would be aluminum oxide. The reason we don't put anything else in the name, like you think carbon dioxide is a molecular compound, and we have the di there for 2 in dioxide, that's because molecular compounds can form many different combinations. With ionic compounds, we're understanding that Al2O3 is the definite ratio that ionic compound will form. So there's no reason it's like redundant to add a di or a tri to that. We're just going to literally name it cation, anion, aluminum oxide. Some other examples, AgF is silver fluoride. CaCl2 is just calcium chloride. K2O is potassium oxide, and NaBr, sodium bromide. So we have an example here we're going to look at, this sample problem A. We're going to look at how to combine zinc and iodine, as well as zinc and sulfur. So recall that zinc from that table, and you have this table in your reference sheets under common ions. You can go ahead and look at that and see that zinc has a +2 charge. Iodine also on that sheet, but you can also think of your periodic table. Iodine in group 17 will have a -1 charge. So again, do the crisscross where they take each other's charge as their subscript. Zinc will take the +1 or the -1 charge and have a 1 as its subscript, and then iodine will take the +2 charge and have a 2. So it's ZnI2. Again, that's telling me that I have one zinc with a +2 and two I's with a -1. +2 balances out with -2. Zinc and sulfur. Zinc has a +2. Sulfur has a -2. When I crisscross those charges, though, I get Zn2S2. That's not the lowest ratio. Lowest ratio would just be ZnS. You can remember that because they are a perfect match. Whenever they're a perfect match, +2 and -2, I can just put the two cation and anion together. So you can see that Zn +2 and S -2, the +2 cancels out with the -2. So those are my two answers for the formulas in sample problem A. Now I do want to remind you about what's called the stock system. That was what I was mentioning earlier with the Roman numerals. We know that some ions, like iron, can form either iron 2 or iron 3. Copper is like that. Copper can either be copper 1 or copper 2. But that's how we say it. We don't say iron +2. We call the ion just iron 2 or iron 3. And that tells me, that specifies for me which ion is in the compound, because different ions do have different properties. Iron 2 oxide acts differently than iron 3 oxide, for instance. So my example here with chromium can be different ions, but specifically because it's chromium +3, I know that that's chromium 3. So we'll just write out chromium with a Roman numeral 3. And the fluoride is just fluoride still. So my name of that compound for Cr+3 and F would be chromium 3 fluoride. That's the name. The formula, because I have a +3 and a -1, I'm going to need 3 fluorides to cancel out the +3. So it's going to be CrF3. Notice I just flip-flopped my charges, and the -1 becomes the subscript 1, the +3 becomes the subscript 3. So it's chromium 3 fluoride with the formula of CrF3. So those are all single elements that involved ions. Recall that we also have polyatomic ions, meaning more than one atom are involved. So a couple examples here, I have what's called nitrate, which is an N attached to 3 oxygen atoms. And the overall system there has a -1 charge. Nitrite also has a -1 charge. It's a nitrogen attached to 2 oxygen atoms. One pattern you might notice when you look at your table of common ions is that 8 will always have, the suffix 8 will always have more oxygen attached to it than ite. Now, sometimes it's not the case that the 8 has 3 oxygen atoms. Sometimes you'll see that the 8 has 4, for instance, with chlorate. or you might see it with phosphate has a different number of oxygen atoms. But the general rule is, as we go from lowest to highest, we go from oops. So if with I have chlorate, for example, here, um, the lowest one with only one oxygen atom attached, we call hypochlorite. With the next one up, we would just call chlorite with the ite suffix. The next one we would call ate with the ate suffix. And then the next one goes perchlorate. I assume this is short for hyperchlorate because you have hypo, ite, ate, and then per-ate. So notice we can have 4 different numbers of oxygen attached to a chlorine. That's the order that those go. Now, for this class, you won't have to memorize those. You are given a table of common ions that you can use if you ever forget that pattern, but I just wanted you to be aware that there is a pattern in naming these. Here's a table of common ions you can look at to see some of those, like chlorite we just talked about. Notice we don't use a whole lot of positive polyatomic ions. Ammonium is the most common one we'll see. Some of those other ones, acetate, always looks a little complicated, but that's the acetate ion. I just see your nitrate, nitrite, sulfate, sulfite. Those are some other ones you will use a lot. Carbonate, phosphate, etc. So it's the same idea when we're coming up with the formula for polyatomic ions as it was for the binary compounds. We look at K2CO3. We know that the cation is named potassium. And the anion, when we see CO3, we can refer to our table of common ions. CO3 is called carbonate. So this substance is going to be called potassium for the cation, carbonate for the anion, potassium carbonate. Notice this ratio that had to be K2CO3 because K has a positive charge, CO3 has a -2 charge. When I flip-flop those, I get K2CO3. So that was my formula. The name is potassium carbonate. See some other examples involving polyatomic ions here. We have potassium sulfate would be K2SO4. Potassium nitrate, it's a plus and a minus, so it's KNO3. Notice that the ions are going to be not moving from one polyatomic ion to the next. They still form their own identity. So for instance, ammonium sulfate, NH42, I had to put parentheses around it because otherwise it would say NH42. And we need to be aware that the 2 applies to every atom in that polyatomic ion. We also have NH4NO3. Notice I don't need parentheses for NH4 when it's just a 1-to-1 ratio. So finally, we're going to kind of wrap up with this last one. It involves both the stock system with Roman numerals and a polyatomic ion. Tin4, that Roman numeral actually makes it nice because that tells me I have tin with a +4 charge. Sulfate, I might forget, so I can go back and look at my table of common ions. Sulfate is SO4 -2. So sulfate is SO4 -2. I can do my crisscross, and I get SN2 SO4. I'm going to need the parentheses 4. However, that's not the simplest ratio. The simplest ratio, because it takes 2 sulfates to cancel out 1, 10, 4. The simplest ratio would be 1, 10 to 2 sulfates. So SnSO4 2. So you can do the crisscross method. Just keep in mind that you will need to reduce it to the lowest ratio. So that was a lot jammed into this 25 minutes, but I have a couple questions for you talking about which compound here does not contain a polyatomic ion. So see if you can figure out which of those does not have a polyatomic ion. And also, can you give me the correct formula for ammonium phosphate? Then with this one, can you give me the correct name for NH4CH3COO? And then with this question, which of the following is the correct formula for iron 3 sulfate? So I wanted to give you some extra practice there. And